Our first speaker is Kushik Viswanathan from Bangalore, ESC, and he will be talking about probing the complexities of interface sleep in frictional sliding.
Okay, good evening. It's nice to be here back in Chennai again. And thank you so much for the opportunity to present some of our work today in front of you. My name, as I was just introduced, is Kaushik Viswanathan. I'm a faculty in the Mechanical Engineering Department at IISc in Bangalore. And our group is technically called a manufacturing group, but we do a lot of mechanics, mostly continuum scale mechanics, fracture, failure, things like that. So hopefully there'll be a different perspective to some of the talks that we had earlier today. Okay, the basic context for the talk is sliding friction. And we all know sliding friction very well. This is an image of the Himalayan fault that runs across, at the foothills of the Himalayas. And the basic premise, there are lots of geologists in the audience today, is that you can get slip at these faults, and consequently you can have slip events, and these emit seismic waves, and you feel them as earthquakes and so on. And right from this scale, which is very large, all the way to something very small and relatable, I suppose, the mechanics of what happens when these bodies slide turns out to be remarkably similar. So if you ask the question, how a body actually slides, right? I mean, the textbook answer that I suppose all of us are familiar with was given by Coulomb, Amontones and Coulomb. And of course, this says that if you increase the load, let's say you're trying to slide this body and this guy is kept stationary. If you increase the load being applied to the left from 0 onward in the positive direction towards the right, then the body remains stationary until the load reaches the static friction threshold, at which point it starts moving, right? This is the classical Coulomb friction model. And it's characterized by this sudden onset of slip at this particular value. This F is given by the friction coefficient times the normal load. Now, this is not this is obviously not the entire picture. And we know, for example, from the vast earthquake literature that there are a whole range of these slip events that happen, and they're not all happening continuously, because if it was happening continuously, we'll all be moving around. And so there is a power law distribution, the Gutenberg-Richter law, from which the Richter scale is derived, as some of you are probably aware. And so that tells you that there is some inhomogeneity associated with this process, right, inherently. What people commonly do, at least in the engineering literature to a large degree, and also in some of the physics literature, the geophysics literature, is you start with these two bodies as being completely rigid, and you postulate that the friction law at the interface is not this Coulomb friction, but it's some velocity-dependent rate and state type of law, right? So you postulate the existence of an internal variable, usually called an aging parameter, and you either have velocity strengthening or velocity weakening, depending on the physical system. Again, all this is done at the continuum scale. And this is used, for example, to explain things like stick slip, frictional slip and stabilities and so on. Now, the situation, there is a different dimension to the situation, and that came about in the year 1971. And there was a paper by a gentleman called Adolf Schalamak. And this was perhaps for the first time that the compliance of the system or compliance of the elastic body became important, right? People knew that elastic systems have compliance, and so when you slide, some degree of that elasticity is going to be, going to show up in the actual sliding process. But the demonstration was done very dramatically by Schalamak. What he did was very simple. He had a hemispherical lens, he had a rubber, piece of rubber, and he'd slit the lens on the rubber. And the lens being transparent could be imaged from the top. And if you looked at the interface, the contact interface, you will see that there are lots of slip precursors that propagate past the interface, and this is what causes slip. The common analogy for this is if you take a carpet on the floor and you want to move the carpet by some amount, you can either slide the entire carpet along, or you can create a loop in the carpet and kick it all the way to the front, right? And these waves of detachment, he called these waves of detachment, they've been called Schalamak waves ever since this paper came out. And they've been observed in a lot of these soft materials, soft systems. So that really begs the question, when does this elasticity become important, right? I mean, on the one hand, you can make the friction law more complex and have rigid bodies. On the other hand, you can make the friction law simple and make the elasticity more accurate. So when does this type of distinction, when is it important? Now, it's critical to realize that there are two time scales in this problem. So let's say you're pushing with some velocity v naught, and the length of the interface is L, there is something called a slip time, which is the length of the interface divided by some typical elastic wave speed. So this could be the Rayleigh wave speed or the shear wave speed in the material. They're all of the same order of magnitude. So we'll assume one of them. When you divide this, you get a velocity scale. And in most common situations, the time scale for this slip is much lesser than the experimental time scale, the time scale for observations. So what you see as being instantaneous is in reality not, but appears instantaneous because the time scale for that is very small. Now, there are obviously two ways to increase this time scale Ts. You can either make the length of the contact very long, or you can make the elastic wave speed very small. In earthquakes, the first thing happens, the length is very long. And in very compliant materials and soft materials, the elastic wave speed goes down because the modulus is lower. Right? When that happens, the Ts goes up, and at some point when it becomes comparable to the experimental time scale, the interface dynamics becomes important. So it's no longer just a rigid block with some friction law, but it's an elastic block potentially with a complicated friction law that you have to work out. And people have found, I'm not citing some of the literature here, but there is at least a couple of decades of experimental observations where people have reported rupture fronts at the interface causing nucleation to slip. Okay, so the static body starts sliding, some rupture happens, and then when the rupture propagates to varying degrees under various conditions, the body starts sliding. That's the common picture that people have. So the work I'm going to describe will be in two parts. The first part is going to ask the question, what types of fronts can occur at the interface? This is work that's already been published, so I'll go over it a little bit quickly. I'll give you a reference to some of the details. The reason I've included it is because the second part depends on this. So in the interest of continuity, I have to give some of these details. And when discussing what types of fronts can occur, I'll talk about some in situ imaging experiments on a typical prototypical soft contact. And we'll discuss what sets the velocity scale. It turns out that that's a non-trivial question. And we'll discuss some properties of these rupture fronts or waves. And I'll very quickly sketch out a theory for the propagation of these waves. Okay, this theory is, again, like I said, this stuff is published. The theory is, severely limited. We'll see the limitations. And that leads to the second part, which asks the question why they occur, right? And for this, I'll describe a lattice model. This work is not yet published. There is a preprint to which I'll put a reference out. And the idea of using a lattice model is to look at finite dimensions and the role of boundary conditions and use that to determine how these waves nucleate. That's a very difficult problem. Even if you go back to fracture, Griffith theory tells you that a crack will propagate at a certain stress. You have various variations of that. But what forms the crack is a question that's very hard to answer. Right? The nucleation problem is very difficult to address. The propagation problem is much easier because you can throw electrodynamics at the problem. And we'll see that as we go along this path, when we do this some of these lattice dynamics calculations, what appears to be a friction problem starts transitioning into an explicit fracture problem, and then that starts branching out into other domains. I'll give some details of this at the end. There are lots of very interesting analogies. We have not probed all of them yet. Hopefully there will be some point of discussion based on some of these ideas. Okay, so the first part is to talk about what fronts we see, and the emphasis is on the word see. Hopefully why this emphasis is on the word see will be clear a little later on. And this is the reference for this work. So here is a basic experimental setup. So we want to slide two bodies, and we want to look at the interface and basically observe the dynamics, right? How it starts sliding, what the rate of sliding is, and so on. So here is what we do. There is a rigid body here, a optically transparent body, and then there's an optically transparent polymer that's backlit, and you take a high-speed camera and look at the interface. When you bring these two into contact, there is a slight curvature on the front face, and so there is a line contact initially, and this light gray patch is where if you put a normal load, there will be a patch of contact. So this is like a contact channel, right? So if you look at the camera image, it looks something like this, and you pull or you push with a velocity v naught far away from the interface on the left side. Okay, and that is what you will see. So this region is the contact region. The dark region is out of contact. Right? Again, some of you have probably seen these results before. Please bear with me because I sort of use this to set the stage for what comes next. Okay, so here I have two different conditions. I have a large contact a large normal load, small normal load. The exact conditions don't matter for now, as it will turn out in the second part of the talk. But the configuration is otherwise identical. The velocity on the left pulling remote velocity is slightly larger than the right, maybe 2.5 times on the right. The contact size is larger. The normal load is larger, so the contact patch size is bigger. And it's being pulled at a constant speed. So far away from the interface, the material is moving at a constant speed. So if you observe what happens, and again, this size, there's a scale bar there, tells you the size is about a millimeter, just over a millimeter, the contact width. Okay, sliding is from left to right. So this is what you see, right? If this is just one slip event, there are a few features. I just run this movie a couple of times so that some of those can be appreciated. If you look outside of the contact zone, yes, this is just in contact. So some part of it is in contact. There is an air gap where there's no contact. There is an air gap. So the indenting system is actually like this with a very large radius of curvature. So you put it in contact. So that's what you need that to get the image. Otherwise, you'll get a patchy image. If you look at points that are outside the contact, they move at uniform speed. But then, for example, if you look at this point within the contact, it remains stationary until this detachment zone goes past it. Right? And now it jumps by a certain amount. So it's here, the wave comes, it jumps to here. Yeah, so you can see that the interface remains stationary until the wave comes, and then once the wave comes, it jumps. You change the normal load, change the velocities. Again, details of how much it's reduced and so on are second order information right now. But if you change that and do the same experiment, you will see something very different. Again, you slide in the same direction, but now you see a wave go in the opposite direction, right? And just keep your maybe eyes peeled out on this point, which is initially here, now it moves here. So the point is moving in the direction you're moving the body in, but the wave is going the other way, okay? And there are two distinct types of waves, right? The features are different, the wave speeds are a little different, and so on. Now, the key sort of message that I'd like to sort of get across here is that the two waves, you can construct what are called space-time diagrams for these waves. You take one location on the interface and stack up images of the same location as a function of time. In this case, it's stacked vertically. And you can measure the slope, it will give you the velocity. The key feature is that both of them travel much smaller than the Rayleigh wave speed. Right? Now, you would expect if there is a slip event, and elasticity is the one that's dominating these slip events, you would expect some correlation with the elastic wave speed. In this case, the generalized Rayleigh wave speed, or CR. But it's not true. Okay, both waves go much slower than the Rayleigh wave speed. The other feature that I also want to perhaps highlight is that both waves show distinct force signatures. So if you just take the overall force, remember this is a velocity controlled experiment, the total force is an integral of the shear stress on the interface, and it oscillates like this for I'm calling the plus wave the one that goes in the same direction as motion, and the minus wave is the one that goes opposite. Right? And the force traces are very distinct. In the second case, you see it starts falling off. Eventually, the contact patch starts narrowing, even though the normal load is kept the same. Now, the question that comes up naturally is how do you explain these types of waves? If you assume, let's say, something like this, your body is assumed rigid. The indenter or the rigid cylindrical piece that is kept in contact is kept assumed rigid. The elastic medium, is, let's say, going from z equal to 0 downward, and it's being pulled, like I said, the same boundary conditions. We're drawing a 2D cross section of it. Usually, when you talk about wave motion, you have a wave equation, which is a hyperbolic PDE. So in 1D, you have something that looks like this, right? And phi could be sound, pressure. If you have a longitudinal sound wave, it could be E bar, B bar, and so on. But there's a wave equation, there's a wave speed. Now, in elasticity, there are two wave speeds, as most of you, I'm sure, are aware. There is a shear wave and the longitudinal wave, or the tangential wave and the shear wave, CT and CL. And they're both for this material of the order of 1,000 meters per second, right? But our waves go at about 100 millimeters per second. So it's several orders of magnitude slower. This is a rubber, yes. There is also a viscoelastic timescale effect. They are lower, yes. So this one is hardened, so the cross-linking density is higher. So it's about 800-ish meters per second. So it's order of magnitude, right? But typically, if you have a very flexible rubber, you're looking at a couple of 100 meters per second. Now, the problem with trying to recover these types of waves from elastodynamics is twofold. Firstly, of course, the wave speed is very low. So there's really not much you can do because any wave that you try to describe with this elastodynamic framework will depend on those two wave speeds. The propagation speed will depend on those two wave speeds. And the second problem is we don't know how they nucleate. Right? This is really the key that we're trying to address in the second part of the talk. So the initial conditions for how these waves form, we don't have much of an idea based on these experiments. We've gone to the side edge of the contact and see how they form and so on. So we have some idea, but then to really get a full picture, you need to look at the cross section. So you need to look at this plane. We're looking at it from above, right, in the experiments. And this plane is very hard to access because the indenter has a curvature, right? So it's difficult to get the initial conditions for this wave problem. I'll describe what we did, and then I'll sketch out, some loosely sketch out the basic procedure. It's not that the derivation is not interesting. It's just, I think if we go over the details, we'll probably spend 80% of the time on 20% of the talk. So I try to avoid that to do this. If you look for elastic solutions that are decaying from the z equal to 0 plane from here, again, we assume this is two-dimensional plane strain. So that's an inherent assumption in this entire thing. And you separate out the nucleation, which means you're looking at a steady-state propagating wave. So you move to a co-moving frame with the wave speed c. Again, there is no a priori reason for the wave speed to be small or large. But nonetheless, just assume there is some wave speed. And the wave speed is a signed quantity. So x plus ct will be in the negative direction, x minus ct is in the positive direction. And we separate the problem out into two parts. We have a region where there is separation. So now the interface is from, let's say, this is in some angular coordinates, but let's say from minus a to plus a, you have a detachment in the middle. And then to the left and to the right, it's remained, the interface remains stuck, right? That's what the experiments tell us. And so we try to put that in to the actual equations and try to model it explicitly, right? So in the separation region, which is in the middle, you have detachment. That's the dark band that propagates. And in the detachment region, you don't have stresses. So it's a stress-free boundary condition. You can change the sigma zz and put an adhesive stress. It doesn't change too many things at the end. But nonetheless, if you assume that it is stress-free here, and it is stuck outside of the contact. So everywhere outside the little separation zone, you have zero velocity, right? Not zero displacement, zero velocity. That's important. And the hat denotes that these variables are at z equal to 0, the plane. The basic idea, the only sort of perhaps non-trivial idea is that we use this C by CT and C by CL as a perturbation parameter, small parameter because it's very less compared to 1, and we do an expansion. This is a singular expansion problem, so you can't set C equal to 0 because that will mean no wave and the whole thing will break down. Nonetheless, you can still do small C by CL perturbation with the understanding that you never reach the C equal to 0 limit. Okay, so that's something that you have to keep in mind. And if you do that, you can reduce this to something called a singular integral equation. You can define the velocity field in the region that is separating. Now remember, the separating region is moving. The stuck region is stuck. So the velocity there is 0. But because the separating region is moving, there is some local interface velocity and the stress is 0. Right? And you can replace the interface velocity in terms of two unknown functions, phi and omega. And you can write down dual series equation, and then you can do a transform and bring it down to this form. If you've done fraction mechanics, you've seen this type of procedure before using complex functions. And these two are called integral equations. They're not just integral equations because, of course, phi appears in the phi and omega are unknown. You're trying to find the interface velocities. So they appear inside the integral and outside, and these two are coupled. So you have to solve them simultaneously to get phi and omega. They're not just any ordinary integral equations, but they're singular integral equations because the integral contains a singularity in this term. So when xi appears, when eta comes close to xi or xi comes close to eta, xi is the variable being integrated, this term will blow up, right? And likewise, this term will also blow up. So there's a special class of these integral equations that you can solve using complex functions. if you make the approximation that the solid is incompressible, which is you send the longitudinal wave speed to infinity, the perturbation series in C can be terminated at the leading order in C by Ct. C by Cl terms go to 0, but C by Ct doesn't, right? And that's the distinction you have to make. If you put C by Ct also equal to 0, the whole thing will blow up because it's a singular problem. If you do that, then you can decouple these equations. So when the material is incompressible, you can decouple the two equations and you can get the phi equation separately, omega equation separately. You have auxiliary conditions. These come from some, this comes from the total load and this comes from some compatibility with the remote velocity. These equations you can invert in closed form with the cotangent kernel. It's a well-known singular integral equation that can be inverted in closed form. And it gives us some solutions, right? I won't write down the solution, but I'll tell you what the solutions tell us. Okay, there are three parameters. There is the dimensionless wave speed, which is C by V naught. V naught is the speed at which you're pushing, right? And there is a wave number, which is V naught by C delta x. Delta x is the amount of slip that a single wave causes. And there is a dimensionless shear stress, of course, this is normalized by the shear modulus. If you put a constraint that the velocity of the displacements have to be, at least the material velocity and the material displacement has to be in the same direction as the remote velocity, you will get a bifurcation diagram like this. Okay, so the first sort of takeaway is in the electrodynamic equations, you do all this stuff that I just described. You will get two wave solutions that have detachments. So one will go this way, one will go this way. And both cause slip in the same direction. Just like the experiments, both cause slip in the same direction. The wave speed, so the inverse wave speed is plotted here, are symmetric. So in principle, both waves travel for a given tau r remote shear stress. Both waves travel at the same speed. Of course, as tau r approaches g, the linear elasticity assumption breaks down. So this section of the curve is a little bit hypothetical, but nonetheless, you get two solutions of the equation. And each wave, as you saw in the experiments, contributes to a slip event. So interface is stationary, wave comes, interface jumps, stops again, wave comes, jumps again. And the theory also predicts the same thing. So if you have the plus wave, the remote velocity is like this. The wave is going from left to right, just like the applied velocity. And this is the slip, interface slip. This is the displacement. So the amount of slip moves towards the right. So the left region is slipped, right region is unslipped. This is the extent of the wave. And T naught is some non-dimensional time. And similarly for the other wave, you get the opposite. Now slip again is positive. Notice that ux by delta x is positive, it's not negative. So it slips in the same direction as V naught. But the slip starts occurring from the right end as opposed to the left. Okay. So again, these two are symmetric solutions coming from the same electrodynamic model. And the slip occurs only during these wave motions. Otherwise, it remains stationary, as you can see here and here. Okay, now the big thing that came out of this, which is what led us to the actual second part of the work, is that if you look at the stress field at the tip of the crack, tip of the wave, we have the displacement, so you can use Hooke's law and calculate the stresses. The stress field shows a divergence. So the region in between here is the crack, the wave, the plus wave or the minus wave, doesn't matter, both are identical. Ahead of the crack, ahead of the front edge and ahead of the back edge, you have a normal stress singularity. And you also get a divergence in the shear stress. Okay, and the nu equal to half is an analytical solution, which is green. And this also becomes singular. And the nu equal to 0.2, 0.35 and so on are numerically calculated. And they also appear to diverge as you come close to the crack tip, the wave tip. The interesting thing is that this exponent for nu equal to 0.5 is minus half. So the stress field looks exactly like what you would see ahead of a moving crack, like for this pulse, which is maybe in hindsight a little bit, intuitive, but then it seemed very unusual when we saw it first. Okay, so I'll summarize this part before I move on to the next one. So there are two types of waves, right? There's plus wave and minus waves. They have opposite directions of motion, and the slip that they affect is in the same direction. They have to slip in the direction in which they're being pushed. They have distinct force signatures, and both travels at speeds much less than the Rayleigh wave speed, right? The model we get two wave solutions from the same elastodynamic model. Singular limit in the wave speed, C by CL can't go to 0. C by CT can't go to 0. It's exactly solvable for the incompressible case. You do numerics for the compressible case, and then you can get the stress ahead of the tip and so on. And it looks like there is some crack type behavior at the tip of the wave, the front tip of the wave, right? Because the stress becomes singular. Yes. The applied velocity. The applied velocity is the only other scale in the problem. They don't exist. This is harmonic, right? The transients are all gone. There are no transients. If you think about it in this problem, the velocity scale is put in artificially because, we went to co-moving coordinates. We didn't talk about how the wave is nucleating and so on. So we force the velocity scale to be set by the displacement rate, right? So it's a little bit ad hoc in that sense. But nonetheless, if you do that, you will get this singular stress field at the tip of the crack. This is the prologue. Okay. Now the main question which I want to get to with this as background is why these fronts occur, right? And this is the result of some numerical calculations. The model is not very sophisticated. I'll go over that in detail. But before we do that, let's step back a bit and look at this friction fracture analogy a little bit more carefully, right? So let's say I have a body like this and I want to push it from left to right. Okay, assume the bottom body, the gray one, is rigid, doesn't matter. Okay. Now, what's the difference between the one on the left and the one on the right? Right? The only difference between them is the boundary condition being applied on the top block happens on the left here, it happens on the top face in the right image. Right? Now, if you think about it, when the body starts to move, if you were to zoom in, let's say microscopically, let's say it's a very nice system and there are no contaminants and so on, you zoom in all the way at the end at the interface, the body will start to move when contacts start breaking at the static friction threshold. So when mu equal to mu s times n, when F equal to Fs equal to mu s times n, body starts sliding. Right? That's what we know from Coulomb friction. In the fracture problem, we know that when the stress, at least in LEFM, we know that the stress, when it reaches the critical stress, the Griffith stress, the mode 2 stress intensity factor reaches the critical mode 2 stress intensity factor, crack starts growing. So already you see that there is some type of loose analogy between the two cases. Now, it's important to understand, and we stepped back and thought about this a bit, but why these waves form, and we know that, okay, if they're propagating, we can describe how they propagate. But the application of the load should matter, right? So let's say I have three cases. I have one case where I push on the left edge. I have one case where I slide on the top edge. And I have one case where I pull from the right edge. Okay? If the body on top, the bottom body is always rigid. If the body on top was rigid, then all three cases are identical. It doesn't matter, right? The net force will be on the right. If you're applying a displacement, the net displacement will be to the right. And it will be integrated over the entire. If you apply small amounts of displacement here and everywhere, it adds up. So for a rigid body, the three cases are absolutely identical. They're not analogous, they're identical. But if the top body is elastic, again, if you go back to that slip time scale that I was talking about earlier, and if you have significant elasticity in the body, then the onset to slip is basically analogous to a crack nucleation problem. Again, this analogy is loose at this point. We'll make it a little bit clearer, hopefully, as we go along with some computations. Okay, and for the elastic case, you have to make a distinction between this, and this. Because if the body is stationary just before it starts sliding, the stresses that are developed at the interface will vary from this case to this case to this case. Okay, it's understandable. And so the three cases should be different. So to look at where these onset events happen and what types of onset events happen and why they happen, we sort of resorted to a lattice model. And the idea again is very simple. I'll just give you the basic outline of what this lattice model does. So there are bulk bonds. So the bottom and the top are both elastic. We make the bottom pseudo-rigid by increasing the stiffness significantly. The ratio of the stiffnesses are about 1:100. Each node has, it basically sits on a triangular lattice and you have this type of connectivity, 60-degree bonds. And there is a normal stiffness and then there's a tangential stiffness between each node, each pair of nodes. Okay, and you need both of these because you have to fit two elastic constants, the Young's modulus and the Poisson ratio. So this allows you to do that. But if you had just one spring, then the Poisson ratio will be fixed for a given Young's and a given lattice orientation. Now we can fix both independently by changing these two parameters. Now at the interface, we put interface. So these are all bulk bonds. At the interface, we put interface bonds, right? And the interface bonds are different from the bulk bonds because they're single springs and they have an initial rest length. The value of the rest length doesn't matter because it just decides how close or how far away these bodies are. And that determines the time step for the computation and so on. But it's a minor detail. But as the top nodes, the bottom nodes are all kept fixed. So the bottom rigid body is kept fixed. And as the top nodes move, either up or left or to the right, these bonds stretch. And as the bonds stretch, there is a restoring force, which has components Fijx and Fijy, Ij being between the ith node and the jth node. And at some critical length, critical extension, the bond breaks. Okay, so that's how we simulate these contact break. It's a very simple model, but you will see that it gives very interesting results. So the equations we solve for are fairly straightforward. This is a completely linear system. We put in some damping to make sure that elastic waves don't amplify and the system doesn't become unstable. There are three force terms. There is, of course, what's called the bond force. Is called a bond model. And these are forces between neighbors on the ith particular node. This is an external force. So whether you apply a normal load at the top or sliding load or whatever, those come in here. And then there is the interface force. So this one doesn't apply to bonds in the bulk. It only applies to bonds at the interface. And we do three different things just to see what happens, right? It's a simple model. The idea is simple. We apply velocity on the left. All the nodes on the left are pushed at constant velocity in the first case. We call this pushing. In the second case, all the nodes on the right are pulled at a constant speed. We call this pulling. And in the third case, all the nodes on the top face are given the same velocity. That's the boundary condition, right? Everywhere else, for instance, in this case, on this face and this face, stress-free boundary conditions. And the same thing with this face and the side faces in this case. And the entire system is solved for. Okay, now what happens when you push from the left? I'll play a video that shows you the color variation in the shear stress. Okay, this is the shear stress at every point inside the body, and you will see how it changes. So initially, for instance, at the right end, there is absolutely no increase in the shear stress. And at the left end, the shear stress goes up until the bond here is stretched beyond its breaking limit. It breaks, and then you have a nucleation event. And this continues. So you have the sequence of pulses that form and keep going from left to right. Okay, and time is non-dimensionalized using the Rayleigh wave speed. You can see that the propagation time is really small, 15 CR by L. CR by L tells you how long it will take for a Rayleigh wave to go through the interface, and this is much, much lesser than that because it reaches the other end only at TCR by L of 50 almost. Okay, there are a couple of things I'll point out and we'll quantify them on the next slide. The first is once the wave starts, once a little breaking wave starts, it keeps the stress field ahead of it the same, right? And the stress field propagates. And the same thing happens when the next wave comes, same thing happens when the next wave comes. That's point number one. The second is as these waves come to the other end of the contact, they suddenly start accelerating. So you see, for instance, that goes off, right? And the same thing happens to subsequent waves. As they come to the right end, they accelerate. These are the analog of the plus waves we saw earlier, right? The Shalamak waves that were going the same direction with detachment. You can construct the same space-time diagram for this particular model. Again, these are all bond states. So you take the interface bond from x equal to 0 to x equal to L, and you stack their states as a function of time. So initially, all the bonds are intact. Then these bonds, for instance, at this time, this bond breaks, and the bond breakage propagates as a pulse and goes all the way. The leading pulse, like I said, accelerates as it approaches the right end. Okay, that's a very curious feature that we observe. And this is irrespective of whether you have a large body, small body, big size, small size, doesn't matter. It seems to do the same thing every single time. And at the left end, these pulses nucleate at almost a constant frequency. So the time spacing between these waves is almost the same. So they're generated at a constant frequency. And they all go at a constant speed, right? And the speed, as you can see from the slope here, is much lesser than CR. So they move very slowly until they accelerate at the end. And the moment this guy accelerates at the same time, and then it stops because the guy is gone and continues, accelerates, the one behind it accelerates, continues, and so on. You can take the velocities and see what they scale with, right? This actually answers the question of what sets the velocity scale, because in the theory model, we put in artificially that C by V naught was the actual scale, right? Velocity, applied velocity was the actual velocity scale. But now you see, if you plot this V by V naught as a function of various V naughts, again, this is non-dimensionalized by CR, which is a constant, for over 2 orders of magnitude, the values don't change, right? Blue is the first front, orange is the second front, green is the third front, the third pulse. And the velocities scale exactly with V, which is consistent with what we assumed, but now it comes without any assumptions thrown into the model, right? The pushing velocity sets the scale for these waves, for these. Okay, now let's go back and revisit the stress ahead of the tip. So if you take sigma xy, again, now I've non-dimensionalized it with rho CR square because it's a dynamic stress. There's a propagation happening. And the x-axis is plotted with respect to the x tip 1. X tip 1 is the tip of the first pulse as it's moving, right? That's always kept at the origin. So it's a moving coordinate system that is, the origin is at the tip of the first pulse as it keeps going. And you see that there is a sort of 1 by root r type of dependence. This dashed line is exponent half, minus half. It looks like there is a 1 by root r. And the trend seems to be consistent. This is at a later time after the second pulse is formed. So second pulse forms behind the first. Origin of this is again at 0, which is the first pulse location. This coordinate is co-moving with the pulse, right? And so the stress state ahead of the pulse doesn't change. Now at another subsequent time, it remains the same. Subsequent time, it remains the same, even though other pulses are nucleated behind. So this 1 by root r type of thing appears to be robust as the wave keeps propagating. We can look at sigma yy, which becomes much more interesting. This also seems to be singular. Again, this is a finite lattice, so you can't say if it goes to infinity or not. It won't, because the forces in the bonds are, the finite distance between these bonds. And again, if you look at it in the co-moving frame, the stress falls off. This region is 0 basically because it's behind the wave where it's detached, just like here. The stress initially was very high when the first wave nucleated, but after that, the normal stress is reasonably low, continues to be low. And the same thing happens with subsequent waves as well. Right? Good. Now we go to the second case. If you pull from the right, what happens if you pull from the right? Now you have a wave going the other way. Okay, it starts at the right end, goes to the left. And it shows basically the same characteristics as the other wave, the plus wave that I showed you. And you see that these accelerate as you go to the left. They keep their stress field ahead intact, and then the subsequent waves come with the same basic spacing between them. And of course, the body has moved, right? The applied velocity has gone here. And the interface, you can see it started here. The body is moving. And the interface points are only moving when these waves go past them. Right? So these two waves are analogous. So if I draw a space-time diagram for this opposite moving wave, the negative wave, you will get the same type of features again. There's nothing different here. If you compare it with the one I just showed you, this is just looks like a mirror image of the other. So pushing and pulling are analogous. The theory already showed us that there's this bifurcation symmetric diagram and so on. The numerics, where there are no assumptions, save for the model details, of course, is also saying the same thing. So the nucleation also seems to favor both waves as being analogous to one another, going in opposite directions, causing slip in the same direction. But there's just one more piece that confirms this analogy. So if you calculate the epsilon xx for a moving wave, you can show that the epsilon xx is compressive for the plus wave and tensile for the minus wave, and the sigma xx is basically the same, shows the same trend. One is compressive, other is tensile. Okay, now here is where things become very strange. So remember, we had these two waves going on like this, going in the same direction, detachment, blah, blah, blah. Now what happens if you shear it from the top, right? If you shear it from the top, there are two things. One is this shearing is basically what you do in mode 2 fracture. Right? It's the same configuration. There is an applied load, here is an applied velocity, but that difference notwithstanding, the configuration is the same as what is described in classical Westergaard solutions, right? The second thing is that the interwave dynamics changes completely. Till now, you had slow waves going this way and that way. Wave speed was set by the pushing, pulling wave speed. But now, if you look at this problem, everywhere there is a buildup of shear stress, right? Everywhere in the material. And then at some point, the wave's gone. Pause it. Building up, building up. There's a front that starts at the left. It's gone. Okay? Building up, building up, building up, building up, building up. Breaks, it's gone. Right? And there is some rebonding that happens because there is rebonding in the model, allow for reattachment of the interface. But that happens much after the interface wave is gone. Right? The rupture front is gone. And that basically is like a shear crack. Right? It looks at least like a shear crack. And it travels very fast. It reaches the Rayleigh wave speed. If you look at the space-time diagram, it's basically flat, right? The height between these two is 1. So TCR by L is 1, which means T is L by CR, right? Which is the time taken for a Rayleigh wave. This is the generalized Rayleigh wave speed. It's not the exact Rayleigh wave speed, but nonetheless. Now, there is obviously some rebonding that happens in the model, but that's all subsequent after the wave has gone off. And if you compare this with the other diagrams I've been showing you, you will see the distinction is extremely stark, right, between these two cases. If you calculate the velocity, you will see that this velocity of the front scales with CR. For various values of V0, you will get the same result, right? Irrespective of how fast or slow you shear or top, front will always go to the Rayleigh wave speed. This banding you see is a numerical artifact on how the wave speed is calculated in front, but it actually reaches 1. Okay, let's look at the shear stress side of the crack. There is also a singularity that comes here, but this is where the thing becomes a little bit murky. So this, again, co-moving frames. Now there's only one tip. There are no pulses. There's just one crack tip. So that's the one that's kept at the origin. And you look at the shear stress. The shear stress builds up as a function of time. These colors are all at different snapshots of time. And you see that it remains high. The normal stress falls off again for a dynamic crack moving like that. Right? This is consistent with what you would expect for a dynamically moving shear crack at the interface. Now, the experiments I showed you didn't reveal this particular Rayleigh wave speed crack. Right? They showed you two waves going opposite direction, both had detachment and so on. But if you probe this reasonably carefully and you play around with the parameters a bit, you can, within quotes, see the other wave. Now, there's no detachment, so you have to put cross polarizers into photoelasticity and recover the stress field. But you can see the signature of that in the experiments. So I'll show you one quick video. This is an experimental video, again looking at the same contact interface from before, but a narrow region in the middle. And the color is loosely proportional to the shear stress at the interface, right? It's actually proportional to the difference in the principal stress, but okay, that's approximately equal to the shear stress because the normal load is very low. And blue is low shear stress, red is very high shear stress. And look at these 2 points, right? Again, you're moving from left to right. There are 2 points that will appear behind these red dots, and then they'll get shifted to the green dots as the wave front comes. So the interface stress builds up, and then a pulse goes through, right? And this travels at a much, much higher speed compared to the other 2 pulses. And you can't see this travel because there's no detachment, no significant detachment associated with this particular wave. Okay, so I'll maybe sort of ease off here with some analogies, because I think this leads us to a lot of other interesting domains that perhaps at first sight look completely unrelated. If you look at how a caterpillar moves, it's basically a long elastic body, just like in the lattice. And it's moving on a rigid ground whose modulus is much higher than the elastic body. And it moves by creating these locomotory waves. So you can see a wave going from the tail of the caterpillar, which is here, all the way to its head. right? And when the wave goes, the thing moves, right? You can see that one more wave is coming in. These are slow waves because that's not moving at the Rayleigh wave speed. You can see similar waves in a very different context. This is what is called peristaltic motion in what is called a planarium. I'm not a biologist, but I hope I've got the term right. And they move by doing the same type of motion. They create these waves that go from tail to head or head to tail. And if you dig up some of the literature, is actually fascinating because there are lots of very interesting studies people have done in this community. Here is one by a person called Gray, who has a famous book called Animal Locomotion. And he basically put some of these insects on a glass slide and looked at them from below and then figured out what types of wave motions you can get. And he found that there are two types of waves. One goes plus and goes minus, right? It's a moving elastic body on a frictional substrate, and it moves by these types of wave propagation. And there is another wave in this caterpillars, it's called loping locomotion, which basically has a detachment that forms and goes all the way to the head. So for instance, this is the head, this is the tail. It forms a little loop. These gray segments are off, they're detached, and that loop goes all the way to the head, and the head jumps by delta of how much ever is formed here, right? This is the step length. And so you see some of these analogs in the insect world, which appear to have similar types of features, at least. Maybe dynamics might be different, but they're also elastic. They're also adhesive contacts, and they have rigid substrates, right? So we think there might be something worth studying in this context of these moving waves. So I'll quickly summarize our basic findings. Again, there are lots of questions that are sort of open, which we're still trying to think about. The first thing that is absolutely certain is that the way the boundary conditions are applied makes a big difference, right? And this is something that I think a lot of people have sort of neglected. Perhaps one reason for that is many of these frictional models are one-dimensional, where you can't apply boundary conditions on the top face, like Burridge-Knopf models, and many of their derivatives are one-dimensional. And so this perhaps slipped through the cracks, if I can use that phrase. But it makes a big difference in what type of wave you get. Now, this begs a question, can you postulate a criterion for slip initiation, right? Now, just like I said, the criterion for crack nucleation is a far tougher problem than the criterion for crack growth, right? If you have an incipient crack, you can see under what loading the crack will grow. But given a loading with no crack inside the material, predicting when a crack will form is not very easy to do. And so can you use something like this to give an analogous explanation for slip initiation, which is basically the same problem? The stress intensity factors, there is a technical problem. Again, I don't want to get into these details, but for interface cracks, if you worked out details for moving interface shear cracks, you will often see that the stress intensity factor has a complex exponent, right? And that is problematic because it gives something called an oscillatory stress ahead of the crack tip, which is unphysical because it leads to things penetrating and so on. That comes up in our model as well, the theoretical model. We think that the numerics, the lattice model, doesn't have that artifact. So we hope that we can extract some type of process zone type of interpretation from the lattice model and try to see if we can go back and correct, just like the Dugdale solution for shear cracks, if you've seen it, something like that for the original solution. And like I said, there are many other interesting problems that seem to have the same type of features, which is something that we've been thinking about a bit. The other couple of things we've been thinking about is when you look at this shear crack going in the top loading case, that's more like a brittle mode for the material to move in this case, versus a pulse going at the interface is more like a ductile mode for the material to move. So can we use some analogies between ductile to brittle transitions for extending some of these transitions is another idea we've been playing around with. With that, I'll stop here. Some of this work was funded by grants from SERB and TST. And these are the guys. So this was actually at a outreach event called Open Day at ISC, in case some of you are in Bangalore or plan to go to Bangalore next year. The last week of February, the last Saturday, we open the institute out to everybody. It's free. There'll be a huge crowd, but we have demos that we do and so on. That's a small lathe that we built 3 days before the actual event. And this box had a demo with Rupert's drops. I don't know if people have heard of Sil's Rupert's drops. We got an LPG gas cylinder and made them in our lab the previous night. These are small tadpole-shaped glass drops, and you can hit the head with the hammer, it won't break. But then if you just slip the tail, the whole thing will explode. And, we were just doing some of those demos for high school children. Thank you so much.
Thank you very much for this interesting talk. We have some time for questions, comments.
Kaushik, it's a fascinating talk, and there are many takeaways. There are many conceptual clarity that I also got. So I wonder your last remark you just made, due to two different loading configurations. So I wonder if there is a side loading, and you wait long enough, or your body is large in size enough. Does that transition to what similarly that you observe for on top loading?
That's a good point. We tried that. It doesn't.
It never.
No, and that one of the reasons why this moving object looks so long is to test something like that. And it doesn't seem to happen. Because the nucleation criterion is a very local criterion. And when you top load in shear, right, you top load the body, the stress field is uniformly distributed for the most part. And so the breaking happens. So the strain energy that is stored in the material is extremely high by the time nucleation happens. That's our loose interpretation. Some of the quantification is not here, it's in the archive paper. So that's the loose interpretation, right? The elastic energy that's stored in the material at the time of crack onset is extremely large in the top loading case because the stress field is like that. Whereas if you do the side loading, the localized stress state near the tip is where all the strain energy is. That's much smaller than the other case, which is why we also think the first case, it accelerates very fast compared to the second case.
Okay.
Because the energy release rate is much higher.
Yeah. So is there, that actually brings to few series of questions. So if I may, so there are two things. First, do you incorporate any interfacial law that you mentioned at the onset of the talk, rate state? Is there something there?
There is just a breaking law for the interfacial bond.
What's that?
It's just maximum stretch. So we predetermine delta L for the springs.
So there is no interfacial stress and slip relation.
No, there is a bond. So the top body has a lattice, bottom body has a lattice. The nodes that are closest to each other are connected by bonds initially. And these bonds will break when the length exceeds some critical length.
Right.
And the delta L at which it breaks is the only parameter you need. The absolute value of the rest length doesn't matter so much. So, and we also have a reforming law, which is when the velocity of a node becomes lesser than some value within some tolerance, and the distance becomes smaller enough, it reattaches. So there is adhesion explicitly also put. Otherwise, you won't get reattachment.
Yeah. So this is like a frictional healing.
It is a frictional healing law. It's microscopic frictional healing law.
And so because you have all the quantities ready, strains, the stresses. So did you try calculating exact energy release rate that each time the bulk sends into that crack, and whether there is a critical, but I think hard part may be to quantify the fracture energy at the interface.
That is the problem. That's exactly the problem. Yes. We've calculated the energy release rate. Like I said, loosely it's higher in the sliding case and lower in the other two cases because the strain field is localized near the tip. But calculating the adhesive energy is not easy.
Yeah. Right. Yeah. Thanks. Fascinating talk again.
Thank you.
Thanks very much. Other questions or comments that you would like to address? Please.
Constant emission of slip pulses with some periodicity. Does that also depend just on your macroscopic velocity? Or?
It does. Yes. I didn't present the scaling of that frequency with the applied velocity, but it does. The loose sort of back of the envelope explanation I can give is if you have n of those pulses at the interface, then the slip caused by n of them in time delta t must be equal to v naught delta t, because the total interface slip, total slip remote should match up at some point, right? That's loosely. So L scales as v naught.
Yeah, but you could have spacing that is smaller, but jumps that are larger.
That is something we have not yet explored, actually, because there it becomes critical what you set the breaking load to be and what you set your readhesion condition to be, because that will determine the width of the pulse. And once you set the width of the pulse, the next pulse will nucleate only when the stress goes up significantly for a bond to break. So there is some muddying that happens with the interface law for that particular relation. We're still sort of trying to segregate them out.
Thank you.